So this video follows on from the previous video, which was on NMR spectroscopy, but it was in low resolution NMR spectroscopy. You really need to have watched the low resolution NMR spectroscopy video before you try and attempt anything on high resolution NMR. So please do that. Okay. So let's look, if we just sort of refresh ourselves on what happened whenever we passed, this is a molecule of butanone, through low resolution NMR. So if we can remember, the first thing that it would tell us is how many different groups we have within a particular molecule. So you can see within butanone we have 3 different hydrogen environments, so we have 3 different proton NMR signals. The signals will manifest themselves like we have on the board now. So you'll see that they are at a ratio of 3 to 2 to 3, and that tells me I have one CH3, one CH2, and then another CH3. It will also tell us that our group furthest downfield here is closest to the electronegative oxygen, and our other CH3, which is the most shielded one, shielded by this CH2, is furthest upfield, and then the CH2 itself is in the middle. So that's the information we can get from low resolution. Number of peaks tells us number of different environments. Integration spectrum or integration trace tells us how many hydrogens are in each of those environments. And finally, the chemical shift position tells us the proximity of those environments to electronegative atoms, in this case oxygen. Now if I took the same butanone, the same molecule, and I passed it through a high resolution NMR machine, I will now get this. So it looks a bit different. We've now got what we call a splitting pattern, and you can see that the CH2 group has split to what we call a quartet, so 4 peaks in other words, and our CH3 group has split to what we call a triplet, okay, or in other words 3 groups. Now what additional information does this proton high resolution NMR give us that low resolution didn't? So these splitting peaks can give us information as to what is adjacent to, in this case, the CH2, or adjacent to CH3. And we'll learn how this works in a minute. So, for example, we already know that this group is a CH2. Now the fact that this splits to what we call a quartet, 4 peaks, tells me that it is adjacent to a CH3. So in other words, I now know in my molecule I have a CH2, CH3. Likewise over here, I already know that this peak is a CH3 from what I have up above. It is split to a triplet, so that is adjacent to a CH2. Now we'll have a look as the slides go on how we actually work this out. So what actually causes this splitting is what we now need to know. So the splitting of a particular signal, okay, so for example, the splitting of the signal on the right into a triplet, why does that happen? So that depends on the number of hydrogen atoms bonded to the neighbouring atom, in this case the neighbouring carbon, okay? So the hydrogen group is said to be coupled with hydrogen atoms on the neighbouring atom. And we follow what's called the n+1 rule. So the signal produced, in other words the triplet or the quartet or whatever I had on the previous page, by a hydrogen group which has n atoms on its neighbouring atom is split into n+1 signals. So let me maybe take a photograph of that. I'm going to flip back to the previous slide and show you how that applies to what we're actually doing here. Okay? So to see where these signals come from, this I already know is a CH3 from what I did up here. This has now split to a triplet, so therefore using the n+1 rule, n+1 is 3, triplet, so therefore n, which is the number of hydrogens on the adjacent environment, must be 2. So therefore I now know I have a CH3 adjacent to a CH2. If I look at my CH2 group, I already know that this signal is generated by a CH2. It is split to 4, which is called a quartet. That tells me that n+1, the splitting pattern, is 4, so n equals 3. So in other words, the carbon adjacent to the CH2 has 3 hydrogens on it. So, and there's a CH3. So that confirms that I have an ethyl group, or a CH2, CH3. So that's your N+1 rule, guys. Really important whenever you're working out what splitting patterns actually tell us. So, if we look at splitting patterns and how we actually look at some sort of we can see that in low resolution NMR we only ever get a peak like we have on the left. Every single peak is like that. But in high resolution NMR it's more complicated. So we will have, for example, this peak here. That's the simplest peak we would get in high resolution NMR. And that's described as a singlet. And that tells us that N+1 is 1 singlet. So the number of hydrogens on the adjacent carbon must be 0. If we have this, which is called a doublet, N+1 is 2, so the number of hydrogens on the adjacent carbon must be 1. Triplet and quartet. Hopefully you're starting to get it now. So we can tell from this splitting pattern of a particular signal how many hydrogens are on the adjacent carbon. Now, you need to be able to at least sketch peaks representing singlets, doublets, triplets and quartets. So make sure that you know the ratios of them. Now, an examiner is not going to get out a ruler, but they are going to look at them by eye and check that you are roughly 1-to-1 ratio, 1-to-2-to-1 or 1-to-3-to-3-to-1 ratio. So please just make sure that you can do that. So if we took for an example of our butanone that we had earlier, we can see that my CH3, my highest shielded CH3, is of course going to split to a triplet because it's adjacent to a CH2. We can see that my CH2, which is here, is adjacent to a carbon with 3 hydrogens on it, so it's going to split to a quartet. And my CH3 here, okay, is going to split to a singlet because my carbon here has no hydrogens on it at all. Right, so I want you to maybe pause the video here and pick up what these are patterns that you will see commonly in A-level questions, and what information does that tell us about the structure of a molecule. So if we look at the first one, if you want to pause it and then I'll go through them. You've got 2 doublets. Well, that tells me very simply that I have a CH beside a CH. Now, what W, X, Y and Z are, we don't know. I have 2 triplets. That tells me I have a CH2 beside a CH2. I have a triplet and a quartet. Tells me I have a CH3 beside a CH2. So that's the ethyl group that comes up commonly. I have a triplet and a doublet. So I have a CH2 beside a CH. And I have a doublet beside a quartet. So I have a CH3 beside a CH. So these are all sort of patterns, guys, that you want to start picking up whenever you see them. Right, splitting by OH groups and NH groups by the hydrogens in here, right? This is dead easy. I'm not really going to go into this in any particular detail, but the key thing from your perspective is they don't split. NH groups and OH groups are always at A level singlets, okay? Now they can split on occasion, but it requires particular circumstances and conditions for that to happen. We don't get those at A level, so don't worry about it, okay? The reason why they don't split is because these hydrogens are what we call labile hydrogens, and that means basically that they are coming and going, leaving and rejoining the oxygen or the nitrogen. That bond is constantly being made and broken, and it's made and broken so quickly that the NMR machine basically cannot pick up any coupling, any splitting pattern, if you like. Now, you just need to know that they only split to a singlet, okay? So, for example, if I have CH2OH, and if I draw that out, just to remind you, a lot of people might think that this should split to a triplet because we have 2 adjacent hydrogens, but because the oxygen is there, it just splits to, in this case, a singlet. So be aware of that for your NHs and your OHs. Right, so if we have a look at this, okay, I want you to explain the NMR that we have below and how it correlates to the structure of the molecule that we have above. So first of all, you might explain that you have got 1, 2, 3 different environments. The next thing you might explain is that this one is going to be a singlet because it's an OH group and doesn't undergo splitting, and it should be way downfield because it's adjacent to an oxygen and close to another electronegative oxygen, so it's highly deshielded. This hydrogen here is adjacent to this carbon, okay, and this carbon, excuse me, okay, not adjacent to that carbon, that's the carbon it's attached to. It's adjacent to this carbon, which has got 3 hydrogens on. So this one's going to split to a quartet. This CH3 group here is adjacent to the middle carbon, which has got 1 hydrogen on it. So that's going to split to a doublet. Okay. This single hydrogen here we would expect to be in the middle because it's close to the electronegative chlorine. So it's going to be in the middle, all right. And on the top end here, this CH3 is the most shielded, and we would therefore expect it to be the most upfield, which it is. Right, so there's 3 molecules on the board. I want you to pause the video and I want you to answer the questions. How many signals should we have? What's the area under each signal going to be? What are the number of hydrogen neighbouring hydrogen atoms, and how does that affect the splitting? In terms of shift, probably at the minute, if we just say which signal is going to be the most downfield and which signal is going to be the most upfield. Upfield being closest to your TMS, downfield being your high chemical shift values of your heavily deshielded protons. So, you pause the video, I'll go through them then. So the first one, we're going to have 3 signals. We're going to have a 3, a 2 and a 1. The neighbouring hydrogens are so we're going to get splitting patterns of triplets, quartets, and we're going to get singlet. This is going to be the most downfield, and this one will be the most upfield. Okay. Next one, we're going to have 4 signals. They're going to be in a 3 to 2 to 1 to 3 ratio. Those are our neighbourings, and they're going to split to a triplet, quartet, quartet, and a doublet. Okay. The most downfield one of all of those is going to be the carbon which is attached to, or the hydrogen which is attached to a carbon which has a chlorine on it. So we're going to have here, this is going to be most downfield, and the most shielded one is going to be this one, that's going to be the most upfield. This one, I'll draw this out because this one can cause a bit of challenge. Okay, so we'll draw C out. We have a CH3, a COO, CH2, a CH2, and a C with 3 CH3s around it. So in terms of environments, we're going to have 1, 2, those 2 CH2s are in different environments, and all of these CH3s are in the same environment. So we're going to have 1, 2, 3, 4 environments. The area under those peaks is going to be, we're going to have a 3, a 2, a 2, and a 9. The first one, A here, if you like, the splitting pattern for that is going to be a singlet because the adjacent carbon has no hydrogen, so that's going to be a singlet. The second, B, we have no hydrogens on the carbon on the left hand side, but we have 2 on the carbon on the right hand side, so that's going to split to a triplet. Environment C, if we look at the carbon on the left, okay, we have 2 hydrogens on that, and if we look at the carbon on the right, there are no hydrogens on that, so that's going to split to a triplet also. If we look at the CH3 groups, the adjacent carbon is this carbon here in the blue circle now. There's no hydrogens on that, so again that's going to split to a singlet. The most downfield one will be the CH3, I think, on the left, so that's going to be the most downfield, close to the oxygen. I don't think B would be the most downfield because it's going to get a bit of shielding from the CH2 and the alkyl group to the right. The most upfield, the most shielded group in here is going to be those CH3 groups on the end with all the carbons around them. So again, if you pause the video, have a look at the question, see if you can do it, or have a go at it at least, and then I will go through it on the screen. So if we look at the first question here, we're going to have 3 signals. So this structure here could potentially be Y. It's definitely not X. We're going to have three signals in a ratio of 3 to 2 to 1, which also fits for Y. And we should have them as a split, as a triplet, as a quartet, and as a singlet. And our singlet should be way downfield, which fits pretty well there as well. Okay, and we have a quartet there, and we have a triplet there. So everything in trace Y looks like it might be A, but we'll go through the others and we'll just double check first of all. So let's draw this one out. This is an ester. Okay, so we have two environments. Okay, so maybe X. There's a CH3 here and a CH3 here. So the integration spectrum will be 1-to-1 ratio, which is X as well. Okay. One of them is going to be more downfield. This one here is beside the oxygen, so it's going to be more downfield. So this one looks like it is X at the minute, but again, we'll go to the next one and we'll double check. Let's look at the next one. So we have here we have 1, 2, 3 environments. They're going to be in a 1 to 2 to 3 ratio, so that's the same as Y at the minute. Okay, now let's look at our, so this one here should be a singlet. Okay, this one here should be a triplet, and this one here should be a quartet. So that's exactly the same as Y as well. So this one could potentially be Y also. So let's go and look at the chemical shift position of 11.7. Well, the only singlet that would be an 11.7 would be from a carboxylic acid. So therefore, that tells me that this one, A, is Y, and this one is not Y. Our singlet here, which would be ester singlet, okay? If I can find that. It's going to be in and around 3.7 to 4.1 for our ester singlet. Okay, so that's definitely not going to be Y. All right, hopefully you're able to work those out as well, guys. Okay, so we'll do a few questions here and then we'll see how we get on. So we're going to do a few questions here, and this is where we'll actually find out if you understand the material or not. So probably a good idea if I put the question up, you pause it and then have a go at it, and then I will show you how to solve the problem. You have a huge book to the past paper questions as well, coupled with this, which you can have a go at. So the first one, which one of the following factors determines the chemical shift? Well, very simply, it's very kindly A. It's the chemical environment of the hydrogen atoms, and basically how close or how far away are they from electronegative atoms, and how shielded or de-shielded are they. Number of peaks that you would get here with low resolution NMR. Okay, well, you would get a peak there. Those two CH3s are the same. These two CH2s here are different. So you would get, sorry, they're different. How am I doing that? Okay, so you will get 1, 2, 3, 4 peaks. It asks you about the spin-spin splitting then of A. Well, there are no carbons on this side, and there is one carbon on this side which has 2 hydrogens on it, so that will split to a triplet. Explain the difference between high and low resolution NMR. Well, very simply, you're talking about high resolution giving you spin-spin splitting patterns, which allows you to work out how many hydrogens are on the adjacent atom in a molecule. Number of peaks here, we have a CH3 here and here. They're in exactly the same environment, and we have the same here. We have 2 CH2s which are in the same environment, so we're going to get 2 peaks there. State and explain the splitting pattern of B. Right, so if we go to the left of B, we see a carbon which has no hydrogens on it. And if you go to the right of B, we have a carbon which is a CH2, but that's the same environment, remember. So an environment does not split itself, so therefore that will split to a singlet. Explain the term integration curve. Well, that's just a curve plotted onto an NMR spectrum, which tells you the number of hydrogens in each environment, or the simplest ratio of hydrogens in each environment. The integration ratio of the hydrogens here, well, in group A we have 6 hydrogens, and in group B we have 4, so we're going to get very simply a 3:2 ratio. Identify a solvent that could be used. Well, we said earlier in the low resolution spec that you could use deuterated trichloromethane, and I would suggest that you stick with that one. State the number of peaks in low resolution spec of this. Well, this, we're going to have that one. There's 1, 2, 3, 4, 5. They're all different, so 5 there. If we look at this one, we have, I'll just draw it out so we can see. Always, if in doubt here, guys, always draw them out. Okay, so that's definitely going to be one on its own. These 3 CH3s are all in exactly the same environment, so we're getting 2 peaks. Name the structure of the compound used as a standard in NMR, well, that's TMS, okay, and it's TMS, not TMC. It's a silicon with 1, 2, 3, 4 CH3s. I'm not going to draw them all in. 2 reasons why that compound is used. Well, it has 12 equivalent hydrogens, so that gives you a very good and strong peak. Okay, and it also has all of those hydrogens are, I suppose I said again, they are all equivalent. Okay, so that gives you a sharp peak, okay, and a strong peak. Actually, this is the strong peak, and this one here is the sharp peak. The other things about it, it's inert, so it doesn't react with your sample. And the other thing about it that you could say is that it absorbs frequencies well outside of the normal range of protons in organic molecules, so it doesn't interfere with your trace. Describe and explain the appearance of the NMR of this. Okay, so let's just put in our carbons here and our hydrogens to make it a little bit clearer for everybody. Okay, so that and that are in the same environment, and this are in the same environment. So you're going to have 2 signals. Okay, the integration trace of those is going to be 1 to 1 because I have 2 protons in that one and 2 protons in my CHs in the middle, so we're going to have 1 to 1. My spin splitting, this hydrogen here is on an OH group and this one's on an OH group, so they only ever split to, as you know already, singlets. This environment here, which is the same as this one, is adjacent to a carbon with an oxygen on it or no hydrogens, and the same here, so that will also split to a singlet. Okay, and these ones here, the OHs, will be by far the most downfield. It's sort of probably between 10 and 12. Okay, and these ones here will be the ones that are more upfield because they're less de-shielded. Okay, on the axes we've got to sketch the expected proton NMR for A, including the integration trace. Right, CH3 here and CH3 here are in the same environment. Okay, and so we'll call that X, and this is in its own environment. So we're going to have 2 signals. Okay, we are going to have a ratio of 6 to 2, okay, or 3 to 1 is what we would put onto our spectrum. Okay, the most de-shielded, the one closest to the will be the CH2 because it's got this on one side and it's got this on the other side, whereas the CH3 groups just have an oxygen here. Okay, so it's going to be the most de-shielded. They're all going to be singlets because this carbon here is beside a carbon with no hydrogen. Sorry, same here, same here, same here. All beside carbons with no hydrogen. So let me get this right. So we're going to have 2 singlets. Okay, the CH2 one is going to be down here, so it's going to have peak integration. Okay, and our CH3 one is going to be there. Both singlets. I'm going to draw a peak integration on that at 1 and a peak integration on that as 3. Which amine has 3 peaks in the NMR? Well, let's look with methylamine. Okay. Okay. So methylamine will have hydrogens there and there, so that's only going to have 2 peaks. trimethylamine, let's do that one. Trimethyl, sorry, that should be a nitrogen in the middle. Well, that and that are all equivalent. That's only going to have one peak. Diethylamine, okay, let's do that one. Diethylamine is here, so we're going to have there and there, they're equivalent. That and that are equivalent. There's 2 peaks so far, there's 3 peaks on that one, so the answer has to be C. Which one of the following shows the correct spin splitting pattern for propanone? Let's draw it out. This is a nice simple one. Okay, so we've got that and we've got that, so we've got 1 peak. They are both adjacent to a carbon with no hydrogens on it. So we've only got 1 signal. It's a singlet. So the answer is A. Which one of the following is B? So we have a quartet, we have a singlet, and we have a triplet here. So let's go through and see what correlates. So we have 4 signals. First of all, that's one. Oh, sorry, we have 3 signals. First of all, so let's go. This A has got 1, 2, 3, 4 signals. So I'm not even going to draw A out. B has got 1, 2. It's an ester, so these 2 groups will be different as well. 4 signals also. Let's get rid of B. Let's look at C. Okay, I think C is going to have 3 signals. It is. So it's going to have this, this, and this. Okay. It's going to have a singlet, and that singlet is going to be here. Okay. Now that singlet is going to be more shielded. Okay. So if we look at the quartet that would exist in this one, that's going to be the quartet in this molecule, and that quartet should be the most downfield because it's right adjacent to the electronegative oxygen. So that should be your most downfield signal here. So this is looking like it's probably going to be C. Let's just check out D. So D has got 1, 2, 3 signals. Okay, so that's fine, that correlates. It's going to have a singlet here, but we know that singlets for carboxylic acids are way downfield at sort of 10 to 12. The singlet in this one is upfield at about 2, so that correlates to the answer being C and rules out D. NMR, okay, 2 isomers of NMR which have a triplet, a singlet and a quartet. Right. So first thing I'm thinking here, that's going to be a carboxylic acid, okay, or ester. Right, so let's have a look. We've got 2 isomers. We have to have a triplet, a singlet, and a quartet. Let's go for the carboxylic acid. First of all, with 4 carbons. We'll see how that leaves us. So that gives us a singlet. It gives us a triplet. No, because this one here is going to be 3 on this side, 2 on this side, so that's going to give me a sextet, so it isn't going to be that carboxylic acid. It would have been nice if it was that. So let's go down the ester route. So we've got 4, so let's go a carbon there and a carbon there, that's 3. Let's put another one there. Okay. See how that leaves us. So we have here 1, 2, 3 peaks. Well, that's fine. We should have 3 peaks. We should have a triplet. We should have a quartet, and we should have a singlet. Okay, perfect. That's one of our answers. Let's go and have a look at another one. So let's turn it to this. See how that leaves us. Again, we have 1, 2, 3 signals. This is going to be a singlet, so that's okay. This one's going to be a quartet, that's okay. And this one's going to be a triplet. There you go. Those are your 2 possible answers. 2 isomers molecular formula like so. They are esters, okay, that's good of them to tell us. Okay, and they both have singlets, okay, in a ratio of 3 to 1. 2 possible structural isomers. Okay, so we've only got 2 different environments here, and we've a lot of carbons and a lot of hydrogens, which would suggest to me we're probably going to have something Okay, so there's 2. We've got 4. We've got all our oxygens are gone, and we've now got down to 4 carbons. So I'm going to go with a carbon there, and then I'm going to go 1, 2, 3. I'm going to go carbon, carbon, carbon. Let's see how that leaves us. So in terms of peaks, that is 2 peaks. We're going to have 1 peak here and 1 peak here. Yeah, these 3 CH3s that I have here are only going to give me 1 peak. Okay, we're going to have 3, 6, 9 in that, and we're going to have 3 here. So that's a 9 to 3 ratio, which is a 3 to 1 ratio. There you go, that's the answer to one of them. Let's have a look at the other. Okay, let's do this and hope that we're lucky. Okay, that's that. Okay, so again we're going to have 1, 2 environments. This one's going to be a 3 and this one's going to have 9. So we're 3 to 1 ratio again. There you go, there's your other answer. Describe and explain the NMR of each of the following. Talk about spin splitting, peaks and integration trace. Right, these should be fairly straightforward. OH. So we're going to have 3 peaks. We'll call them A, B and C. Spin splitting, this is adjacent to a CH2, so it's going to spin split to a triplet. That's adjacent to a CH3, so that's going to go to a quartet. And that's an OH group, always goes to a singlet. Peak integration, we're going to have a 3, a 2 and a 1. I think that's everything done. Let's do ethoxy ethane, not on the spec, so maybe you want to look the structure of this one up. It is as so. Okay, so that and that are the same, we'll call them A. And that are the same, we'll call those B. Okay, so let's go first of all, spin splitting. This environment is adjacent to a CH2, so A is going to split to a triplet. B is adjacent to a CH3, so they're going to split to a quartet. Peak integration is going to be, we have a 6 to 4. Okay, so 6 to 4, 3 to 2 ratio is what we will have. These ones here would be, I don't think it asks for chemicals, yes, they would be the more downfield of the 2 peaks. Okay. So in this one we have a infrared spec, which they pop up now and again. Okay, so you have to look at your table for your infrared specs. We have got this formula here, so we have 2 oxygens in it again. So it's either going to be an ester or a carboxylic acid. See if they give us any other information. The relative integration values as so, deduce the structure, both explain your deduction. Okay, so we have here, if we look at our NMR, that's a C double bond O, and if we look here, we can also see a C single bond O. So that's going to suggest to me that we have an ester here. Okay, so C double bond O, C single bond O, and an ester, as you know. Okay, we have 4 carbons, all right, so, and we have got 3 environments here. So let's go with that. Okay, so let's just check and see how that leaves us. So here we have a it's going to split to a triplet, that's going to split to a quartet, and that's going to split to a singlet. Okay, that looks pretty good. Yeah, that's exactly what we should have. Our peak integration should be 3 to 2 to 3, and we're 0.8 to 1.2 to 1.2, so that's the same, 3 to 2 to 3. Okay, so yeah, I think that's definitely going to be one of our answers. Let's take our ester and flip it around then. So let's go 2 and see if that is successful. So here we're going to have 3 environments again, so we're going to have A, B and C. We're going to peak integration of 3 to 2 to 3 again, okay, which is what we should have. We're going to have that split to a triplet, that's going to be a quartet and that's going to be a singlet. There you go, there's your other environment, or sorry, your other structure there. So it's ethyl ethanoate and methyl propanoate are your 2 structures. Okay, which one of the following gives spin-spin splitting and integration trace of 2-chloropropanoic acid? Well, let's draw that out first of all. So 1, 2, 3, propanoic acid is there, OH there, 2-chloro is there. Okay, so we are going to have, what are we after? Spin-spin splitting. So this one's going to split to a 2, this one's going to split to a 4, and that's going to split to a singlet. So we have a 2 and a 4 and a 1. Well, in actual fact, there's only one of them that gives us that integration. No, sorry, splitting. Ignore that. That's spin-spin splitting. My integration is going to be a 3, a 1, and a 1. Okay, so my only two possible answers are those two, and in those two we're looking for a doublet, a quartet, and a singlet, so the answer has to be B. State why there's a signal. Well, that's your TMS, your internal reference is what you would call it, as well as saying it's TMS. Explain why the signal at 1.15 is a triplet. Let's just draw this out so we can show it. We have an amide here. Okay, so it is a triplet. It is this signal here, and it's a triplet simply because it's adjacent to a CH3. It's a CH2 adjacent to a CH3. Explain why the signal at 2.25 is a quartet. It's a quartet. Sorry, that was wrong. That last one was my mistake. Apologies. Ignore that. The triplet is a CH3 adjacent to a CH2, of course. Okay, got that the wrong way around. The answer to that, the one I just gave for B, is actually the answer to the next one. It says, why is this one a quartet? And that's because it is a CH2 adjacent to CH3. Explain why the signal at 5.5 has the highest chemical shift. Well, it is the highest chemical shift because these are these hydrogens here, which are adjacent to electronegative nitrogen. So they're mostly D-shielded. Explain 3 ways in which the spectrum of N-methylated compound would differ from this spectrum. So the N-methylated compound. Okay, so let's just draw that out. So we're comparing this, okay, to the same molecule, but this time it would have an H on it. Okay, so because of this, it's going to have an additional signal. So it's going to have +1 more signal, okay. What else are you going to have? So you're going to have one more signal. That is going to have an integration trace on it of 3, okay. And it is not going to be split. It's going to be, that is going to be a singlet. Okay. What is meant by a triplet in NMR? Well, a triplet is just simply 3 peaks, and it tells you that whatever you've got is adjacent to a CH2. Okay, guys. Hopefully that, coupled with your past paper question book and the answers to those, will allow you to get a decent understanding of high resolution NMR. Hope that helped. All the best.